Good day. In previous video, we discussed about what is meant by potential energy approach. Today, we can solve the problem with the aid of potential energy approach in finite element analysis. Example problem is assemble equations of equilibrium for the spring system shown in figure. Okay, so the spring system in following figure by direct approach, so that minimization of potential energy also yields same result. So this problem objective is compare two approaches. One is direct approach, another one is potential energy approach, how the results came. Likewise, the examination to be conducted with this problem. Here the problem spring system, already I told you what is the spring system this problem has. Let's see the spring 1. Okay, the spring 1 has the stiffness of K1 and it consumes force F1. Okay, after that the spring 2 also has its own stiffness which is nominated as K2 and it exerts a force F2. And the spring 3 also has its own stiffness which is K3 and it exerts the force F3. Likewise, the spring arrangement is available. So, if I apply the force on the spring means it may give some deflections. Based on the deflection, we can define the stiffness of spring. So, due to the stiffness, the spring exerts the force. So, from the force, the displacement happens. So, from the force 1, the displacement is known as u1. From force 2, the displacement is u2, and force 3, the displacement is u3. Likewise, the problem has the data. Now, how can we solve? Yes, here I can proceed with the delta 1. Delta 1 is the load applied due to the load, how much of extension it carries out. Likewise, I can assume here you see delta 1 happening in the region of the spring 1. The spring 1 make the displacement of u1, so that the delta 1 extension is delta 1 is equal to u1. After that, the spring 2 load, I mean force 2, which deflects something. Okay, so which means delta 2 here, the u2 is available. We can subtract what is the exact value of spring 2. So the u2 minus u1, because the spring 1 and the spring 2 connected with the serially. So if I want to measure the spring 2 displacement means u2 minus u1, I can find the exact spring 2 deflection. So delta 2 is called as u2 minus u1, and automatically we can move to third spring, because in this series connection there is third spring is also available. The third spring has its own stiffness which is K3 and which has its displacement u3, and I want to identify the deflection or extension means delta 3 is equal to u3. The third spring displacement is u3 and the second spring displacement u2. When I subtract u3 with u2, I can get the exact spring 3 extension. So delta 3 is equal to u3 minus u2. Likewise, I can collect the data from given problem. After that, what is the next step? By direct approach, draw the free body diagram. What is the rule for draw the free body diagram? Draw the object of interest. Object of interest here is the spring 1. It has two connectivities. How the force is exerted with the spring 1, I can identify. So, draw all forces acting on that object. So, if I consider the first spring has the force from left hand to right hand, and from the spring end to towards right hand side. So draw forces acting on the object. Here object is spring, and resolve all forces vectors into x and y components. Let's see, I can explain with some example. Here you see the node, the circular element is node. After that, what I do? Yes, in the left hand side there is force is acting which can be denominated as like K1 into delta 1. As like our potential energy approach, the deflection is multiplied with the load into deflection. After that, what happened with the right hand side? Yes, here after completing of the first spring, the force is moved to second spring, so that K2 into delta 2. What happens on this node? Yes, due to this the applied force, applied load only, this kind of the extensions are occurred, so that we should consider about the force F1. So the free body diagram, what are all the forces acted on this region is the force acted from the spring 1 and the force applied onto the spring 2, and in between there is force 1 available. So I can represent the free body diagram with all the forces acting on the object like this. The same is followed for second node. Here you see the three nodes are available, 1, 2, 3. What happens with the second node? Here the second node acted with the second spring's load, so K2 delta 2, and right hand side what happens, this second spring exerts its force on spring 3, so the spring 3 has its some own deflection, so which can extension which can be represented with the delta 3. So left hand side I can multiply K2 with the extension of the second spring, and in the right hand side the third spring stiffness into the extension occurred with the third spring. Here the force is called as F2, and then third spring I individually consider the third spring. The third spring which can be has only the K3 delta 3 element, and the third node has its F3 only. Not the third spring exerts any force on further elements. There are no further elements. So here I leave next term, right hand term. So this third node only has its left hand side force and the common force F3 force. Okay, this like this we can draw the free body diagram for the corresponding problem. After that we can frame the generalized equation from equilibrium condition. How can we frame the equations? The equations of equilibrium are according to the first free body diagram. Here you see the node available. The first force K1 delta 1 acts towards left hand side, apart from the body and this node, and which can be acted on opposite side to that right hand side, so that which can be represented with the negative symbol minus K1 into delta 1, and then the another force which can be acted on right hand side, which is second spring K2 delta 2, so that which can be represented with the positive symbol plus K2 into delta 2, and force F1 is also acted on right hand side, not in left hand side. So here also I can utilize the positive symbol, which is plus F1 is equal to equilibrium equation, means here I can put 0. Likewise I can frame the equation. For example, if I consider the second free body diagram, here what happens? Here you see the left hand side force is K2 delta 2, but it acts on left hand side rather than right hand side. So here I can put negative symbol for K2 into delta 2. And what happens with the right hand side? Plus K3 into delta 3, plus here what happens with the force? Yes, the force is also acted on right hand side, so that plus F2 is equal to 0. And then finally, what about the third free body diagrams, equilibrium diagram? Yes, here only one force is acted, so from the node which can be acted on left hand side only, so that minus K3 delta 3 I can represent. After that force 3 with the third node is acted on right hand side, so that plus F3 is equal to 0. So the initial step is equilibrium equation formation and free body diagram drafting. After completing this, we can utilize these extension equations which are delta 1, delta 2 and delta 3, and equations of equilibrium for further solutions. Here I consider the framed three equations which are equilibrium equations, and the notations, which means displacement equations. Delta 1 is equal to u1, delta 2 is equal to u2 minus u1, delta 3 is equal to u3 minus u2. Here, from the mentioned equations, we can write. How can we simplify this? Yes, we can see. According to the first equation, k1 into delta 1. What is delta 1? Here you see u1 available, so that I can represent, I can substitute the delta 1 is equal to u1 in the particular equation, so that minus k1 into u1 plus next k2 into delta 2. What is the value delta 2? Delta 2 can be represented as u2 minus u1, so that I can substitute here u2 minus u1 for delta 2 plus f1 is equal to 0. Likewise, we can substitute these three displacement notations with the available equilibrium equations, and then I consider the second equation. Here delta 2, delta 3 terms available. I can substitute delta 2 is equal to u2 minus u1 on this equation, and delta 3 is equal to u3 minus u2 on this corresponding equation. From this I can get minus k2 into u2 minus u1 plus k3 into u3 minus u2 plus f2 is equal to 0. Likewise, I can change the second equilibrium equation with the displacement values. After that, I consider the third equation. Third equation has delta 3 and k3. k3 is normally I can recall. And what about delta 3? Delta 3 is equal to u3 minus u2. So that here I substitute u3 minus u2 plus f3 is equal to 0. This is not enough. So I can simplify, because here you see k2 of u2 minus u1 available. Why not? I can multiply k2 with u2, and I can multiply k2 with minus u1. Likewise, I can simplify this equation. Here you see the first equation, I can multiply minus k1 u1, normally I can recall, plus I can multiply k2 into u2 minus k2 into u1 plus f1 is equal to 0. Likewise, I can represent the equation. After that, the second equation, I can multiply k2 with the internal terms and k3 with the internal terms. Here k2 into u2 minus k2 into u1 plus k3 into u3 minus k3 into u2 plus f2 is equal to 0. Likewise, I can restructure the second equation, and then I can move to third equation. Here you see k3 into u3 and k3 into u2 plus f3 is equal to 0. This is not enough, because randomly the negative symbol, positive symbol is available. What can I do? Yes, let's see. Next step, I can move the plus f1 to right hand side of the equation, because here you see the 0 available. If I move the positive f1 to right hand side, means which can be changed as like minus f1. What about the second equation? I can move the f2 to right hand side. Here the f2 can be get minus symbol, but it can be represented with the right hand side of the corresponding equation. And then third, f3 it has, so that k3 u3 minus k3 u2 is equal to minus f3. Likewise, I can rewrite the equations. Not only the equations are enough, okay, so further reduction is also needed, because the equation here you see the negative symbol available, right hand side also negative symbol available. I want to eliminate the negative signs the equation. For the reason, here I can multiply the first equation with the negative symbol. What happens? Let's see. Here I can multiply the minus symbol with this, minus into minus plus. After that, plus k1 u1, and here also minus k2 u2 converted, and here minus into minus plus, so that plus k2 u1 available, and then is equal to plus f1. Here after moving this u1 term, common u1 term I collected from the equation, so that k1 plus k2 into u1. Likewise, I can get the equation k1 plus k2 into u1 minus k2 into u2, because I multiplied this equation with the minus symbol. So here this positive element is converted into minus symbol. Is equal to minus f1 is also multiplied with the minus, so that plus f1 I got. Likewise, I can change the second equation also. Here also I can get the common term, which is u2 from the common coefficient, which are k2, k3. I can convert this equation like this. After that, I can multiply the negative symbol with the third equation. Here I can convert k3u2 minus k3u2 plus k3u3 is equal to positive f3. Likewise, I can change the equations. What is the next step? In FEA, all the calculations we should perform with the matrix formulation, so that I can collect the data from the matrix. Here you see the above equations with the matrix form. Here first 3 cross 3, because the matrix has the 3 elements, which is u1, u2, u3, so that I can get the matrix is in the form of 3 cross 3, because 3 equations I have. For the 3 equations I can frame 3 rows and 3 elements u1, u2, u3 available, so that I can select 3 columns. So now I can pick the u1 coefficient for first row of 3 cross 3 matrix. What it has, k1 plus k2, I can pick from first equation. What about the second u2 term? Here minus k2 is the coefficient of u2, so that I can get minus k2. Here there is no k3 term, I mean u3 term, so that I can present here with the 0, and then I can move to second equation. For the coefficient of u1 is equal to minus k2, so I can represent with the second row of first column. And then what about u2 coefficient, which is k2 plus k3, so I can assign the second row of second column with the k2 plus k3. What about the third? Minus k3 is available, so that in this equation the u3 variable is also available, so that I can assign the minus k3 in the third column, second row value minus k3, and then I can move to third equation, which is minus k3u2 plus k3u3 is equal to f3. Here you see the first variable u1 is not available, so that I can represent 0 for the corresponding place, respective place, as a 0, because in this equation there are no u1 variable, so that here it's 0. What about u2? Minus k3 available, so that here I represent minus k3. What about u3? Plus k3 is available as a coefficient, so in third row, third column I can represent the k3 value. So I can make the square matrix with the 3 cross 3 form, because of I have 3 equations, so I can frame likewise. After that, the variable representation, what all the variables are available, u1, u2 and u3, so that I can form the 1 cross 3 matrix, which is u1, u2, u3 likewise. And then what about the right hand side of these, I mean those equations, is equal to f1, f2 and f3, so that here also I can represent 1 cross 3 matrix, which are f1, f2, f3. Likewise, I can represent the matrix with the direct approach. Which is the direct approach? We can examine the same problem with our potential energy approach. Last video I explained about what is meant by potential energy approach. With this link also you can refer what is potential energy approach. According to the potential energy approach, the total potential energy in the spring is equal to energy stored in spring minus average force during the extension, which can be represented with the notations of pi is equal to 1 by 2 ku square minus ku by 2. Likewise, I derived the equations in my previous video. You can refer that. Now I can utilize this equation for further solving of this same problem with the total potential energy approach. Okay, so the equation phi can be represented with for first spring. Here you see the first spring, what are all the elements which has the first spring, k1 has the first spring has the extension of delta 1. From this we can rewrite, okay, the equation with the potential energy approach as like phi is equal to half into k1 into delta 1 square. The first spring has the force which is F1 into U1, so that I can represent minus F1 into U1 like this total potential energy of spring equation. And then if I move to second spring, means here also 1 by 2 into K2 delta 2 square minus F2 U2. Then third spring plus 1 by 2 into K3 delta 3 square minus F3 into U3. So I can collect the three different springs equations and we can restructure the three springs equation and assemble every spring equation with each other. Finally I can get this equation with the, here you see delta 1 is equal to U1, delta 2 is equal to U2 minus U1, delta 3 is equal to U3 minus U2 available. Because of our free body with the displacement of spring, we can get this information. In first slide I did explain the thing. Okay, now I substitute the values delta 1 here, delta 2 here, delta 3 here. Here I substitute delta 1 with the U1. So of K1 into U1 square is converted plus of into K2 into what is delta 2 U2 minus U1 available. So that U2 minus U1 square plus of into K3 what is delta 3 U3 minus U2 here available. Okay, the square minus F1 into U1 minus F2 U2 minus F3 U3. What is the next step? I want to further simplify this equation from differentiation. Why do I differentiation? The finite element analysis always utilizes the differential equation for getting the exact solution than approximate solution. Reducing the residual, I can move to differentiation. Here the variable, three variables are available, U1, U2 and U3. So the equation, the above mentioned equation is differentiated with respect to U1. So delta phi divided by delta dou phi divided by dou U1 is equal to 0, which can be represented with K1 U1 plus K2 of what happens here, K1 into U1 square. So here x power n is equal to n into x power n minus 1. So which can be converted as like 2 into U1. So I can eliminate 2 by 2 is equal to 1, so that I can get Qa1 into U1 plus what happens with this here also U1 available of K2 into U2 minus U1, the term we can constantly keep. After that this 2 can the same procedure, x power n can be converted into n into x power n minus 1. So the 2 into x power 2 minus 1 is equal to 1. So here the 2 by 2 cancelled, so I can get K2 into U2 minus U1. After that this is solved by differentiated by U1, so that this U1 has negative symbol, so that minus 1 I got. After that F1 U1, this term only has the U1 term. Okay, and after that F2 term does not have U1, F3 term is also does not have U1. So those two terms are got 0, but F1 only available because which has U1. So minus F1 is equal to 0. Now further I can simplify. How? Yes, I can multiply the K2 with the internal terms K2 into U2 and K2 into U1. Likewise I can simplify. From this I can got K1 plus K2 into U1 minus K2 U2 is equal to F1. The same thing I can perform with the first equation is differentiated with the U2 term. Here also I can got the equation as like minus K2 U1 plus K2 plus K3 into U2 minus K3 U3 is equal to F2. The same equation is differentiated with the U3 also. So where the U3 term available, only the third term has. So K3 into U3 minus U2 power 2, so that 2 the same x power n formula, 2 into U3 minus U2 power 1 I got, so that 2 by 2 I cancel, so that K3 into U3 minus U2 minus F3 is equal to 0 I got. From this I can simplify this minus K3 into U2 plus K3 U3 is equal to F3. Likewise I can get the equation. From these three equations I can frame the matrix form. Here you see the first equation K1 plus K2 into U1, so I can pick here, and then second term minus K2 available, so that second row of the second column of first row is minus K2. Here there is no U3 term, so here I represent 0. After that K2 minus K2 available, so I pick. After that K2 plus K3 I can pick. After that minus K3 for third, and the third row 0 according to this term. The initial term u1 is not available, so that 0. The second u2 variable got minus K3, so that minus K3 I got. Here the third, which is K3. After that the variables u1, u2, u3, and the right hand side f1, f2, f3 available. I can restructure it, okay, in the matrix form. So now I got, here you see the term with the potential energy equation this. After that I can refer with the previous step. Here also the matrix formulation has K1 plus K2 minus K2 0. The examine this equation I got from direct approach. Here also I got this equation I got from the potential energy approach. Those equations are have similar, so both equations are exactly same. Thus the condition that potential energy should have extreme value leads to equations of equilibrium. So the two equations are same, the two matrix forms are same from the potential energy approach and the direct approach. So these conditions prove that potential energy should have extreme value, which is minimum, leads to equations of equilibrium, which is the method to solve with the potential energy approach and the direct approach, and compare those results with each other, and we got the solution. Thank you. If you are having any doubts, you may ask me through comment box.